Hey everyone, thanks for checking out my video. This is going to be the demonstration project for Dr. Buckner's class, MAE 535. And today I'm going to be taking a look at a permanent magnet DC motor and discuss a little bit of the theory behind it and how it works. So first let's start off with the theory. So the first equation I have here is the Lorentz force equation, right? Which essentially states that there's going to be a resultant force on charged particle Q when there is a magnetic and electric field, right? However, in this example, there is no electric field. The next equation we have here is going to take out that term, and we're left with F equals the cross product of QV cross B. QV being a charged particle moving at velocity V, B being the magnetic flux density, F obviously being the resultant force. However, this equation can be modified a little bit further. What we get here is F equals IL cross B. I being, the current going through current carrying wire L cross B. And this equation is kind of what helped me visualize or understand what was happening in the demonstration that I'll show you later. So this right here is a little bit, it's just a simple diagram of that equation. You have your current carrying wire going in the positive X direction, magnetic flux density B going up, positive Y. You'll then have a resultant force going out of the page in the positive Z direction. Just kind of a rough sketch to visualize that. So let's take a look at the model. Essentially what I did, I just used some Lego parts I had lying around. Thought it was a good excuse to use them. And I used some paper clips here to kind of supply current to our coil, which is what they will rest on. I have the magnet here in the center just resting, and the battery is underneath this frame that I constructed. So essentially what we're going to do, we're going to test 3 different test cases where I will move the positioning of the magnet. So the first test, the magnet will be where it is right now. The second one, I'm going to move the magnet up here. And then the third case, I'll split up these magnets and put some on the bottom and position some on the top and see if we get any motion. So that's what we'll do. Test case 1. So in this case here, according to the right-hand rule, we're going to have current going in this direction, magnetic flux upwards, which means we're going to have a resultant force in the right-hand direction here. So if we put that theory to the test, what happens, you can see here, it's moving in a clockwise direction, not completely steady all the way, but there you go. It's moving in a clockwise direction, just as the previous equation we discussed would validate. Test case 2. So in this one, I'm going to be holding the magnet above the coil like this. So basically what would happen according to the theory is you're going to have current flowing through in this direction, like the last one. You're going to have flux pushing down on that coil. So what would happen is you're going to have a resultant force in the left-hand direction here, which would mean there's going to be some counterclockwise motion like that. So let's try it out. And there you go, just as the theory would suggest. Okay, so this is going to be test case 3. In this test case, I already have a magnet on the bottom, but I'm going to put a magnet on the top of the coil as well and see exactly what happens. So here it goes. Okay, and as you can see, it stopped, right? Because when you have a magnetic flux going up and down, it cancels out the resultant force, which we previously discussed in the other 2 test cases. So that would line up with what the theory would suggest. All right, so that concludes the demonstration project. I hope you guys enjoyed it. I certainly did. Definitely showed off the principle we discussed in the beginning. And overall, I think it was a success. So thank you guys for watching. I hope you all enjoyed it.